Hello, I'm Mr. Muskeluk, your AP Chemistry teacher at ChemAdvantage.
Here we have a limiting reactant problem, and we're going to use an ice chart, a very important chart that you'll be using for the entire year to solve this problem. You can see the reaction occurring where we've got two solutions, and on mixing they form a white solid, a precipitate. The net reaction involves the lead ions of one solution reacting with the sulfate ions of the other to make a solid. There are a couple of other ions present, potassium and nitrate, but they're just floating around and they're spectators, and we're not going to use them in this reaction. So let's work on the problem. The solutions containing 26.1 millimoles of lead. They're giving you the amount of lead Pb plus 2 in solution. It's a small amount, so we're using milli, thousandths of a mole. And these are the positive charges. The T looks like a plus cations. And then we've got our sulfate ions in solution too. And we have 47 thousandths of a mole of them. And you can see them sticking together to the lead. Now, we're asking, what's the limiting reactant? And let's go to this ice chart to do that. Now, the ice indicates initial. This is chemistry, the study of change, and this is what we start with. And then the two react with one another, the lead and the sulfate, and that's our change. And then when we're done, the change is finished, and we'll see what we have afterwards. On an ice chart, initial, change, and end, and later on this will be equilibrium, we take what we start with. And what we start with here is our lead ions, and we said 26.1 millimoles of them. And indeed, we have that. It's a lot easier writing 26.1 than 0.0261. But you could have solved the problem that way too. And here we have 47.0 millimoles of our sulfate ions. Now, the reaction indicates one lead reacts with one sulfate. Well, 26 leads will react with 26 sulfates, but we have 47 of them. So we have an excess of the sulfate. In other words, our lead runs out before our sulfate does. In a ice chart, when we have both reactants, we find which one we run out of first, and that's going to be the one that has the fewer number of moles when we have a one-to-one relationship. If there's some coefficients here, you divide by the coefficient to find out the smaller limiting reactant. So if the lead is the limiting reactant, it's going to be the stuff that's used up and the amount that's used up. Notice I've got a negative sign here. This is a reactant that is going to be consumed. So we're going to have the 26.1 millimoles of lead sticking to the sulfates that are there. So those lead ions are going to be gone. And in the end, we've got nothing. They will have been used to make the lead sulfate. So that's our change. Lead ions being changed into this solid. So our solution doesn't have as much lead in it as it started off with. But in this change row, and this is important, once you know one of the values, you can find all the other values in the change row using the coefficients. And in this case, we've got a pretty easy setup because we've got 1, 1, and 1. Since they all have the same coefficients, we will all be 26.1. So we're going to have 26.1 millimoles of that sulfate used up and making our lead sulfate. Of course, the lead sulfate we didn't have any to start with, and now we're going to make that lead sulfate. Remember I said coefficients, they all are 1, so all these values will be the same, except this is going to be a plus because we are making the lead sulfate. So in the end, this white powder, when we end up weighing it and separating it using filter paper, we would expect to see 26.1 millimoles of this white powder, lead sulfate. As I said, we had 47. We had extra sulfate, and in the end, our solution in here is going to contain 26.1 minus 47, 20.9 left over. In effect, they've got nothing to react with sulfate ions. So let's look at this again. We're given the amounts. Those were given in the problem. We just plug those in. That's our initial before mixing. And of course, we haven't made any product yet. That's why this is 0. And we found the limiting reactant, and that are bold-faced as 26.1, which we use then to put in the rest of the change, because that's our limiting reactant. We wipe out 26.1 millimoles of sulfate and make 26.1 thousandths of a mole of lead sulfate. And the end is merely the addition of these columns. So the initial we get from what's given in the problem. We use a little bit of reasoning to find which substance is the one that's our limiting reactant and use that for all of our change. And again, you get one of these values in a change, then the rest will come in this case, because we have a 1, 1, 1, they'll all be identical. If this had been a 2, we would have had, 2 times 26, 52.2 millimoles used up. And if this had been a 2, our sulfate would have been the limiting reactant. Okay, this is a very important table. You'll see these over and over again, and you should look at them, and they make a lot of sense. Okay, this is at the end. When we're done, left in this test tube will be no lead, or not a large amount of lead, and some leftover sulfate and our solid that's produced. Now, they give us the molar mass here of our lead sulfate, so we can figure out this mass because they gave us the molar mass. We know moles times molar mass gives us grams, stuff that we can end up weighing. So let me pull the calculator out. Our calculator is here, and again, to get our mass, we'll take our moles times our molar mass. Now, the moles are in millimoles, thousandths of a mole, so I'm just going to write down 0.0261. You could have used 26.1 and then divided by 1,000 at the end, but I'm going to put the millimoles in right now. Milli, 1,000, we move the decimal point 3 places, 0.261 times the molar mass, 303. Don't really need those extra, but I'll put them in anyway. This is the weight. This stuff's stuck here in the water. In order to get this, we're going to have to filter it out, and I'll show that in a couple of seconds. But this is the mass that we would expect, and that rounded to 3 significant digits is because we had our 26.1 millimoles here, is 7.29 grams. Now, if you had forgotten about the milli and multiplied, you would have had 7,920 whatever milligrams, and you just moved the decimal point over because you'd realize, oh, I forgot about the milli. What is the excess reactant left in solution? Well, our excess reactant is our sulfate, and we've already talked about that. That's our 20.9 sulfate. Now, this is the reactant. We still have got potassium ions, which are spectator ions, and nitrate ions. Potassium and nitrates don't form precipitates. There's an exception for potassium, but you don't have to worry about that in AP. But they just float around, and you're not going to be in the precipitate. They're going to be left over in this clear solution. Here's our next thing. We have this white powder stuck in this test tube. To get that out so we can actually weigh it, you dump it into a funnel that has this filter paper, a fine mesh paper. The solution goes through, and the white powder, you hope, is trapped in here. And you rinse it to make sure you get rid of any leftover sulfates and any leftover potassium and nitrates. So you just have the lead sulfate. Remember, we've got extra stuff here. We've got potassiums, nitrates, and sulfates. So once you trap this white powder here, you rinse. In this case, you see they're using a beaker with this little glass rod so that the water runs down, and you wash the precipitate. That's an interesting term. Washing a precipitate is just taking and rinsing it with some water so that it doesn't have anything else in it. This filter paper is empty, and here's its weight, 11.65 grams. When we take this paper and put the precipitate in it and then dry it so there's no water there, we would have just the weight of the precipitate. Now let's see. We've got mass of filter paper and precipitate after drying, mass of filter paper. If you subtract these two, you'll get just the precipitate, the dried recovered lead sulfate. Let me get my calculator out again. This is the paper and this precipitate, the white powder, 17.11 grams. And we can subtract from that the filter paper, which we're not interested in. Just the dry filter paper, 11.56. And we have 5.5 grams that we collected. Now, wait, we should have got 7.92 grams. So we've got some of this white powder that's missing. Experimentally, you'd say, well, what did it? Common answer that's always wrong is human error. You don't want to use that on an AP exam. Don't write it down. Don't waste your graphite or a pen, because that's just going to be something a grader will say -1 point. Not going to get that. You have to come up with a chemical reason, not a human reason, why we're missing some of this lead sulfate. And that's what we're looking for. Now, I've got some possible choices here. If we had filter paper and it wasn't dried completely, our final mass would have been greater. We would have had some water on this filter paper. So that would have given us, if this is like 18, a larger mass. We know that's not a reason. Now, if some of this lead sulfate dissolved, that means some of the lead sulfate got through the filter paper because it couldn't be trapped because it's dissolved, and we'd have a smaller amount left. That looks good. That would be great. Some of the lead sulfate escaped because it dissolved while we were rinsing. Potassium ions and nitrates from the original solution remained in the precipitate. Well, if they stayed in the precipitate, then we'd have potassium and nitrates in here in addition to the lead sulfate. That would make our weight greater. That's not going to work. Excess sulfate trap. Nope, that makes our final result bigger. Not going to work. And then some of the precipitate managed to get through the pores of the filter paper. Well, it escaped, so we had less than we expected. Filter paper comes in different grades. One of the problems with filtering is that it takes forever. You got to get this water to drain through. Let me show you here's one of the techniques for filtering. This is a pretty detailed method of filtering where you take this circle. Filter paper comes in circles, and like I say, various grades, depending on how good of a mesh you want for it. One of the problems is if you have a grade that is really, really tight, doesn't let much through, it takes forever to filter. They have some tips here to make it filter faster. Again, this is a procedure that depends on the school you're working with. But the general idea is you try and get the precipitate trapped into this paper and rinse it so that any impurities go out of it. And here's their rinsing. They're using a wash bottle. They rinse all the precipitate that might be caught in the test tube, in this case a beaker, and try and get it in here. Now this, like I say, is a really arduous and a long process, so bring a book with you if you're going to use filter paper because you want to read a novel or so. In the meantime, there's other things that are a lot more expensive where you use a vacuum and you've got a funnel here that is made out of porcelain or glass, and then you have a circle, and this thing has holes in the bottom, and you end up using a vacuum to draw this stuff through, but still you end up drying some filter paper. Again, this is going to vary from school to school and their equipment. And here's what typically they'll use to dry the filter paper: an oven that's just warm enough to get rid of the water, but not set the filter paper on fire. Now, let's go back to our problem, because there's something we haven't quite answered yet. And that is, what is the percent yield in the experiment? And percent yield says, how good was this? I should have gotten 7.92 grams, but I only got 5.4. So I didn't get all of it. This is going to be an easy one to figure out. You'll just take your calculator and say, hey, I got my 5.55 is what I ended up getting in terms of grams, but it should have been 7.92 grams. Multiply by 100. I'm not going to bother. I just going to move the decimal point over 2 places. 70%. That's our percent yield. The yield was 70%, 70.0, 3 significant digits. We got 70%. So 30% of that lead sulfate somehow managed to sneak through this filter paper. Well, there's our ice chart. And also, we've talked about some possible experimental error, which is not human, where we explain chemically what happened. We had millimoles, we had grams. This is a pretty nice problem. And it's one that you could expect to see on an FRQ on the exam. And actually, I took this partially from one of the FRQs. So good luck. Remember, ice will end up helping you in AP Chemistry.